Hi everyone, thank you for joining us for Post Quantum Computing, what you need to know about the UEFI Forum updates, hosted by the UEFI Forum. We'll get started here in just a couple of moments. Thank you. All right, thanks everyone for joining us for Post Quantum Computing, what you need to know about the UEFI Forum updates webinar hosted by the UEFI Forum. I wanted to introduce our presenters. So we have Jiewen Yao, who's a principal engineer at Intel. Jiewen has been engaged as a firmware developer for more than 20 years. He is chair of the UEFI security subgroup and co-chair of the TCG PC client working group. He's the EDKII maintainer for the security PIC and the crypto PIC. Sean Brogan is a software engineering manager at Microsoft. Sean has been a firmware developer for more than 20 years. He manages the Microsoft Core UEFI team, represents Microsoft in the UEFI Forum, and is actively involved in numerous related open source projects, including Project Mu, ODP Patina, and EDKII. We did just want to provide a quick disclaimer for this webinar content. So just to note, this content in the presentation reflects a point-in-time snapshot of the work conducted by the UEFI security subteam and is subject to change without notice. The published UEFI specification shall serve as the sole normative reference, and this content is provided for informational purposes only and should not be used as the basis for any production implementation. And with that, I'll pass it off to the presenters to walk through the agenda and the slides.
Thank you, Megan. Yeah, it's just a heads up that this is kind of a new content and that we really want to bring the larger community into this. So we are making this content available early. We're opening up kind of our normal process that's normally under NDA. And it's because it's so important. It's because it's a big set of changes and we really want to collect feedback. So as Megan said, it's really important that we don't take this as the final solution. That will be in the UEFI spec when it is released. But this is a point in time, and the process is going to transition into what is known as the code first process, using the EDKII project to kind of drive from here. So there will be changes. What you see here will not be final, but it is, we're getting it out there so that we can collect feedback. So we're going to do a quick introduction. Then Jiewen will go through the changes that we're talking about. I'll come back and give a little bit of update around how Windows has been involved and some of the ideas there, and then we'll finally have a summary and a Q&A. Hopefully, if you're here, you know what post-quantum cryptography is, post-quantum computing. This really isn't going to be a talk about that. It's really about how the UEFI specification is going to morph to support a world where post-quantum computing, is a thing, and we support post-quantum cryptography. In that, the UEFI specification has kind of really been focused on traditionally on the RSA algorithm. We've used that throughout lots of use cases, and you'll see that throughout this and kind of in the future, we are going to a more agile approach so that we can support differentiation here. Also, post-quantum cryptography kind of means something to, it means something different to everybody, and the different governing bodies, the different regulatory bodies. And so part of what we're going to talk about is how are we agile and how do we adjust to the different requirements and make sure that the specification is something that gives us a great framework, but we're still able to adapt and change as necessary as the world kind of changes around us. And then kind of final point of this is we're going to talk a lot about UEFI Secure Boot. That's mostly because that's the main feature that is defined in the UEFI specification that uses cryptography. It's kind of the main interoperability interface that is really critical that we get right, and has numerous players that have to work together. So when we talk about UEFI Secure Boot, what we really mean is, how are the binaries authenticated through code signing? How are they authorized through how the firmware uses the DB? And ultimately, how are they revoked through the DBX? And then finally, kind of how are those databases updated in market, in the field, so that they stay current and stay relevant. Real quick, I think it was important that that we kind of lay out a little bit of the context of where the UEFI security subteam has been thinking about this, and what our goals were. So first, our goals, right? We had to add post quantum cryptography support. It's a requirement. We know it's coming. We need our systems to be commercially viable and able to sell into all the markets that we want to. So we have to add that support. Coincidentally, at the same time here, the original keys that have been widely deployed to support UEFI Secure Boot for the last 15 years are expiring in the next few months. And so throughout that process, Windows and the entire ecosystem has kind of been trying to update these keys for machines that are in market. And throughout that process, we've kind of identified a bunch of challenges, a bunch of inefficiencies and things that haven't quite worked right. And so as part of this set of changes, the sub-team wanted to address a few of those. And then finally, again, UEFI Secure Boot's been around for 15 years. When it was originally designed, there was ideas about how this would work, what would get used. And I think as we reflect back on the last 15 years on how that's really done, we've noticed that there is some additional complexity. There's additional things that are really unnecessary and when unused. And so as we evaluate, how do we move everything forward, we're looking at kind of reducing that and getting rid of some of those. From a principled side, as I mentioned, we're really looking at agility and making sure that the UEFI specification provides the infrastructure that will enable us to be successful in the post-quantum era. This means we're going to stay away from defining specifics and kind of make sure that we have defined the things that allow, servicing agents, operating systems to detect capabilities, and platforms to declare their capabilities, so that we can adjust and move and migrate according to where the requirements and kind of the world takes us. Finally, we're expecting change, right? I think as we enter this, we've been really fortunate for the last 15 years, again, that we've been able to use a single algorithm, essentially a single set of keys. But the expectation going forward is that probably will not be the case. And as we even look at algorithms, the expectation is those may change, or the requirements around those may change over a relatively short period of time. So we want to kind of plan for that change. Finally, some things that are out of scope and, is being very specific about the algorithms. We're also not proposing new primitives and new APIs that are specific to post-quantum. And as much as we are kind of evaluating the whole system and ensuring we have a compatible solution, we're not going to get into spaces that are generally managed by other working groups or other spec bodies like the TCG around measured boot. I think there is a little bit of discussion where we touch how images are actually measured, but for the most part, we're leaving that to the appropriate working groups. With that, I'll turn it over to Jiewen.
Hi, thanks, Sean, to give an introduction. Now let's look at the UEFI spec PQC update plan in more detail. Here's a list for the PQC related change proposal for UEFI spec 2.0. 12 maybe. Then we split the feature into 3 categories. The first category A is a new feature we plan to add. I will introduce them one by one in the next couple of slides. And category B is some old feature we plan to remove or deprecate. The first one is a signature supported variable. Because the scope of current signature support variable is unclear. The UEFI spec does not state whether it's applied to UEFI secure boot only or to any other crypto features in the firmware. As such, we propose to deprecate this signature support variable and recommend use the new ECIT table which we introduced in category A. Second one is a private auth variable. The problem is that there's no spec-defined revocation mechanism for the private auth variable. No mainstream OS has any intention of using them, and the current design allows an attacker to perform a pinning attack against the boot service variable that the OS depends on for security. As such, we propose to deprecate the private auth variable feature. Third one is that we want to remove the variable authenticated 3 descriptor. Today, there's no open source implementation for the authentication 3 exists, nor there's any interest in adoption for the mainstream operating system. That leads to the specification to be misleading, as it informs the reader that they should enroll the secure boot key, use the auth3 descriptor. As such, we plan to remove that. The fourth thing we plan to remove is the audit mode and deployed mode for the secure boot. The current spec describes the audit mode behavior and deployed mode behavior, but that's never been widely adopted. Leaving them in the specification is very confusing. As such, we plan to remove the audit mode and deployed mode from the secure boot state machine and simplify the mode transition for the secure setup mode to user mode only. And category C is something we're trying to clarify or clean up. It does not impact the function. For example, we're trying to clarify that we should ignore the certificate validity check in the secure boot, clarify that all hash algorithms should be included for DBX, and clarify to deprecate SHA-1 since it's been forbidden for a while, and clean up the language that limits the crypto agility. And finally, we're trying to clarify the number of signing in for the auth variable update. Only one signing info for auth variable update is allowed. Let's look at the first feature, multiple signature verification. During the PQC transition time, we expect a UEFI image may need to support multiple signature for crypto agility. This is to allow the image to be verified by old platform or by the new platform which support PQC. As long as one of the multiple signature is validated, then the image passes the verification. However, the current spec says that neither the hash of the binary nor any present signature is reflected in the DBX. The second part, any present signature is reflected in DBX. It blocks the expected multiple signature usages. As such, we're trying to propose to clarify the DBX policy. The verification order should be as follows. So first, if the hash of image in DBX, it fails. And if the hash of the image in DB, it passes. And if any of the signature in DB but not in DBX, it passes the verification. Otherwise, it fails. We also want to mandate the order of multiple signature for verification. We propose to use a top-down mechanism based on the signature in the UEFI image. Here is a figure to show the the P image and how we want to verify that. The left-hand side shows that the image we will calculate image hash, and we also scan the image to find that there are two signatures. Signature 1 is RSA, signature 2 is ML-DSA plus EC-DSA hybrid. The verification flow shows in the right-hand side. First, we check the image hash in DVX. Yes, it will fail. And move the image hash if in DB, then it pass. Then it will scan all the signatures one by one. If any of the signature in DB and it is not in DBX, then it will pass the verification. But if all signatures not either not in DBX or in DB, or they are in DBX, then it will fail the verification. The next part is the DBX, DB and DBX. We plan to adjust the content in DB and DBX. The current status is that DB only support image hash or a full certificate, while DBX will support the image hash, a full certificate, or a to be signed certificate hash. However, we realize that putting a full PQC certificate in DB may cost lots of flash size. As such, we plan to support to be signed certificate hash for DB as well. Also, putting a full PQC cert in DBX may consume lots of flash space and cause problem if we want to revoke multiple PQC certificate at one time, because we want to do algorithm check. So we believe that using a to be signed certificate hash for DBX is good enough in this case. As such, we propose to add TBS certificate hash for DB and remove the certificate support from DBX. The final database may include the image hash. It could be in DB or DBX. TBS to be signed certificate hash. It could be in DB or DBX, and the full certificate is only in DB. And here is a figure to show how we verify the signature according to DB and DBX. With the top-down order, we get the first signature in P image, then check if it matches the to be signed hash or certificate in DB. If yes, then we check if the to be signed cert hash or cert in DBX. If no, then that means we find the image whose signature is in DB and not in DBX, and the image pass the verification. But if the signature is not in DB or it is in the DBX, then we'll skip this signature and look for the next signature. If all signatures are rejected, then the verification will fail. Next one, we know that not all UEFI firmware will support PQC algorithm at one time. That means at some point of time, some of the UEFI firmware will support PQC, but some does not. Now the problem is that what if the OS loader or application may want to know if the UEFI firmware is PQC ready or not. The OS loader or application may choose some security policy based upon the firmware algorithm. Support PQC or not PQC. Today, there's no such mechanism to report which crypto algorithm is supported. As such, we propose to let the UEFI firmware report a EFI crypto indicator table as part of UEFI configuration table and ACPI table. This table will report each individual crypto algorithm used in some specific feature. The scope of the ECIT is that the crypto used in UEFI firmware, for example, UEFI secure boot, host variable, system firmware update, device firmware update, etc. And this ECIT table also supports extension. For example, if the OEM, ODM, or IBV may want to report a vendor-specific crypto usage, for example, the signed recovery feature. Or the silicon vendor can also report its own features, such as Intel boot guard algorithm. It builds the secure boot chain from beginning. This figure shows the reported entries in the ECIT. On the left-hand side, you may find the EFI image verification entry. It shows the PKCS7 algorithm supported in DB. For example, it's only include RSA today, but later we may want to add ECDSA and ML-DSA or any hybrid algorithm. Then it also report the EFI authenticated variable entry. It shows the PKCS7 algorithm in PK and KK. Same, it's used RSA today, and later we may add ECDSA or ML-DSA. So those two entries are using OID to report the supported algorithms. Now let's look at the right-hand side. So ECIT table also include a EFI secure boot authority entry, which report the EFI signature type for DB. The image revocation entry, which report the signature type for DBX, and also the EFI secure boot servicing authorization entry, which report the signature type for KK and PK. You can see that we added the EFI cert X59 share algorithm for DB, and we removed the EFI cert X59 from DBX as we proposed in previous item. On the bottom, the blue item shows the extension, for example, the silicon vendor extension or OEM extension. The owner of this table entry need to define the detailed format in its own specification, but it is not in UEFI specification. Next one, since we are adding new algorithm support, there might be a case that OS want to add a new DB or DBX entry, but the EFI firmware does not support that feature, support that algorithm yet. Currently, there's no algorithm check for PK, KK, DB, or DBX when it is updated. If the signature verification pass is just write to the UEFI variable. The risk is that if a crypto algorithm is unsupported by the UEFI firmware, and the firmware still returns success, which mislead the caller and will cause the image verification fail later. As such, we propose to add text clearly that the UEFI firmware need to check and reject if the updated PK, KK, DB, or DBX include any unsupported algorithms. Of course, the caller can query ECIT table to understand which algorithm is supported. For example, when a DB is enrolled, it will check against PKCS algorithm in EFI signature, EFI image verification entry, and the EFI signature type in secure boot authorization entry. When a DBX is enrolled, it will check the EFI image revocation entry. When PK or KK are enrolled, it will check PKCS in UEFI authenticated variable entry and also the signature type of the secure boot servicing authorization entry. This is to ensure the new entry enrolled will take effect eventually. Since there's a check for PK, KK, DB, or DBX, the caller need to know that which one is not supported if the set variable API returns unsupported. As such, we propose to mandate the set variable API only include one EFI signature list. That means if it's rejected, the caller can know clearly why it is rejected. Note that the final database in DB or DBX or KK, etc., it can still include multiple different entries. The caller can call set variable multiple times, and each time it append a new algorithm type. So eventually, the full database may include multiple entries. And this figure shows the data structure. The left-hand side is the OS2 descriptor, which is used in set variable API. You can see that we want to mandate only one EFI signature list, but you can still have multiple EFI signature data under this one EFI signature list. The right-hand side shows a full image database variable. It could include multiple EFI signature lists. Here it shows that the first list is EFI cert SHA-384, which is an image hash. And the second list is EFI cert X59 SHA-384, which is a to be signed certificate hash. There could still be multiple entries there in the final database. Here is the last feature we plan to add. It is a KEK self-signed append. Today, we know that KEK can only be updated if it is signed by a PK. The problem is that it may cause delay if the OS or UEFI CA issue a new KEK. So we have to rely on OEM to enroll the new KEK signed by their PK, which might be a big challenge for them. As such, we propose to allow a new KEK to be appended if it is signed by an old KEK. That allows the OSV to issue and append the KEK for update quickly and adopt the new image database. This figure shows the relationship of the UEFI image, DB, DBX, KEK, PK, etc. For example, you can see that the DB, DBX is used to verify and launch the EFI image. Then the KEK is used to verify and update the DB or DBX. And the PK is used to verify and update KEK and DB or DBX. With this new feature, we want to allow the KEK to verify and append itself. That is the new part of this relationship. Here is all feature we plan to add. Now let's move to the third part of the presentation. So Sean will introduce the Windows OS update and the UEFI CA update.
Thanks, Jiewen. So I think here what we really wanted to reinforce was that, Windows and in the sub-team, there's been a lot of Linux representation as well. Everyone is kind of behind these, and again, want to reinforce that these are changes that are necessary. They're critical for us to, adapt and move our ecosystem forward. From the Windows side, you will expect to still kind of get your formal communication through the normal channels. For Windows, that's WHCP and HLK. From there, I think ultimately in the coming months, hopefully we will see some algorithm specifics defined there. It's likely that you'll see some sort of requirement on the next UEFI specification, which I assume will be 2.12. Again, making some assumptions here that these types of changes will land in that specification. And you can imagine that if you'd like to have a PC that is compatible with a post quantum, set of keys, that you'll need these changes. And then finally, that ECIT is going to be absolutely critical for Windows to be able to detect this capability. So there's about 3 or 4 points here from the kind of the Microsoft and the Windows side, just again, based on the different roles that they play in this ecosystem and for the UEFI Secure Boot feature. One of the things I wanted to highlight is that for the longest time, and if you still read our published WHCP, you'll see that we require OEMs to ship in user mode, which is Secure Boot enrolled. And that's served well. It has some security benefits, or at least perceived security benefits. But as we kind of look forward and we realize the challenges that poses on an OEM, around figuring out what their user is going to do, what operating system they're going to use, what set of keys they may use. You might manufacture a device in, the July of 2026, but it doesn't get sold until December, and we may have a different set of keys or different capabilities. So we are changing that guidance and kind of encouraging the use of setup mode. Now, there are other options, and through OEM discussions and partner discussions, we can talk through those. But our broad statement here is that we're encouraging shipping devices in setup mode. This will kind of give the capability to reduce the attack surface, right? We kind of mentioned that when this is done in the manufacturing line, the OEM has to kind of put every key in the database for compatibility reasons. Makes perfect sense. We want our users to have a great experience out of the box. But that ultimately has a lot of downstream effects for the lifetime of that machine, meaning that it has a really high attack surface because every key, even if they aren't using it, is in those secure boot variables. It also means that when we service the secure boot variables, we have to address all the attack surface. And so ultimately, it leads to more servicing on that device. When the manufacturing is doing this, they don't know what the user intent is. And again, I'm talking about mass market, selling through, standard channels to consumers where they don't have this intent. And so again, they don't know what operating system the user is going to use, and therefore they have to be in that max compatibility mode. And then finally, kind of as mentioned, our expectation is changing over time, agility here, and doing that at the manufacturing time gives us less agility. To support that, Windows is kind of evaluating. I'm not committing to any of these plans here, but we are evaluating some features to enroll UEFI Secure Boot if a machine is in setup mode. Enroll that during what's known as our UBI or our setup process, so that the machine, before the user ever even uses it, has Secure Boot enrolled, even though it was shipped from the factory without Secure Boot enrolled. There's also desire to bring that capability into Windows. So if a machine doesn't have Secure Boot enrolled, there would be a way for users to do that from within Windows. And then if a machine does have Secure Boot enrolled, we'd love to start showing some of the contents there. Again, just because the world is getting more complicated, and it's important for end users to be able to see how their machine is configured and kind of understand that. Again, these are potential or pending, and I really hope we get to see these, and they will help us move forward. So Windows and Microsoft also, because we manage the KEK that is on most machines, we do most of the servicing across the industry. Obviously, with this more complexity, the servicing agents, the payloads that you can expect, like we probably won't have a single DBX anymore. There'll be multiple DBX payloads, depending on your configuration. We'll have to also be able to read that ECIT, detect the algorithms that you support, and the payload formats that you support, and make sure that we apply the right content to machines. When we multi-sign boot applications like Windows Boot Manager, that'll have to also be accounted for in how we service this. And then finally, there's been a lot of talk around SHA-256 and whether it's deprecated. I think our analysis of this for things like revocation are that there's no need to make a change here. We'll continue to use that, but that's the current plan. All right, and then Microsoft also runs the UEFI CA that signs third-party option ROMs, the Linux shims, and other UEFI applications. To date, because we're already going through this transition from the 2011 key to what's known as the 2023 key, when you make a submission today, we sign with both keys and give back payloads that are signed by both. The expectation here is that any set of active keys, the signing portal will provide back signed payloads that match all of the active keys. So no real change here, hopefully no surprise here. All right, moving on to kind of the summary and call to action, right? I think hopefully everybody saw that there's a fair amount of changes here. And again, the whole point of this presentation was to kind of give a snapshot of where we are in this process, start to gather a broader set of feedback, and invite everyone to join in that process, even those that are not necessarily in the UEFI forum. So there has been, as of yesterday, a white paper published with the same exact content, a little more detail. And then there is been a project set up on EDKII on GitHub that allows us to start tracking and following the EDKII defined and UEFI forum supported code first process. So join us there, as that's where the next iteration of these changes will be and discussed. I think with that, again, this has been, Jiewen and I have been representing the larger UEFI security subteam. There's a lot of members, a lot of people involved from a lot of different companies, and we would like to thank everyone there for their contributions and their help in charting the path forward. I think, Megan, now it's up to you.
All right. So please, if you do have any questions, submit them via the chat feature and we'll try to get to all of them. The first question that we had is, what is the rough target date for the updates to the UEFI specification that include PQC support?
I think I can take this one. I think we're being pretty careful around this, in that, you know, we're not here to represent the forum or to announce any kind of specification release dates. But you know, we are aware of how critical this is, and you know, in some ways even behind a schedule that we'd all like it to be. So we are actively involved in trying to get into the next specification, and I think the forum is kind of waiting for this effort to wrap up before we announce and release the next specification.
Thanks, Sean. The next question is, given the newness of the PQC algorithms and NIST inclusion and backup algorithms, do our standards and implementation support hybrid cryptography to avoid weakening our security posture when adding PQC support?
Go ahead, Jiewen.
Yeah, I'll just say that in our design principle, we're trying to avoid to specify which PQC algorithm we want to support. So the spec will be quite neutral on that area. But from implementation perspective, we are using the OpenSSL. I think probably EDKII we're still using OpenSSL. What algorithm they want to support there, and the way the EDKII can support, and also the UEFI CA can choose appropriate algorithms there.
I think I can add to that. You know, from the Windows side, and again, I think the current plan is that we will be generating some post quantum keys for running the CA. Obviously, signing a Windows Boot Manager. We are at the moment headed down a path using something we're calling composite. This is the ML-DSA 87, EC-DSA, P384, SHA-512. That's a mouthful. But I think, yeah, it's from this talk, the idea really is like, make sure we're agile, because we're going to have to make changes. From a real implementation side, we have the same concerns around these cryptography and ensuring that we have a safe setup, and so there's ongoing discussion here. There's also some challenges around crypto library availability for some of these hybrid algorithms or composite algorithms, but I think that's TBD. We'll see, but that's the hope.
Next question, in the signing signature verification order, will you mandate that the most quantum safe signature is the primary and it only falls back to RSA if the PQC signature fails?
No, this is not what we proposed. We proposed just to use a top-down order on the peak-off image, which means whatever appears in the peak-off image at first, that will be verified first. Because it's really hard to say which one is safer, which one is not safer. Hard to compare.
Adding to that, it's also really important that our PCRs, if we're talking about measured boot, are predictable for features that are using the TPM PCRs for sealing secrets, and so we need to have firmware be very consistent around how it does that and make make the servicing agents that are applying these changes aware of how that's going to be done.
Next question, the PK signs the KEK ESL. So if there's a new KEK, can we sign the KEK.ESL with an old PK and enroll?
With the old PK. Yes, that is supported feature today. The KK can be signed by the old PK. Yes. And the feature we trying to add in the A8, I think it's A8, that we allow the new KK to be signed by the old KK, but it also support to be signed by the old PK. So
does Microsoft have a sense of when UEFI CA will begin signing UEFI device drivers with PQC algorithms?
I don't think I have any timeline to kind of lay out today. I'd expect, again, we have communication through the portal and the blogs there to lay this out. As mentioned, there is some challenges around availability of the infrastructure needed. And so, I think everyone here is working as fast as possible to get that done.
I see that enrolling secure boot keys will be possible from Windows after setup. Will it be possible to re-enroll keys in the same manner? If a user has enrolled the Windows DB only, would they be able to enroll Windows plus UEFI keys later?
So in this feature, there's no proposed change to the roles and authorities of the UEFI Secure Boot key databases, the PKKEC DB. So Windows can't kind of break those rules, and so it kind of I'd say it depends, right? It depends on how and the authority of your PK or KEC. But you can imagine, if we follow the existing pattern where we use some common offline KEC and PK that is not available, then there will not be any capability to do that, because that would be breaking the security guarantees and rules of UEFI Secure Boot.
What is the boot time impact of adding PQC support?
That's a great question. I think that's that's one of the reasons why we want to do this code first and want to get to an implementation, at least a prototype implementation, to see if there's other optimizations needed. There's definitely going to be an impact, and we want to make sure that we minimize that.
What about SBOM? Is this something we need for PQC? And does the BIOS measurements for the secure boot and TPM need any changes for PQC?
I can answer the second half. Should the BIOS measurement for secure boot in TPM need any change for PQC? Yes, I think so. First thing is that since we introduced the ECIT table, probably we want to measure this ECIT table into PCR, into like PCR1, to make sure the ECIT table is not tampered by any other people. Also, the entry in DB or KEK or PK will be updated to support PQC. So you will see a different PCRs, a different PCR value for those.
I think the part about SBOM, I'd say that the SBOM is independent of this. I think it's a great thing, and we should all be looking at that, but I don't think it's going to be impacted here.
Can you explain the feature image verification versus feature secure boot authorization in the ECIT?
Yes, let me go back to that table. Okay, image verification versus secure boot authorization in ECIT. Okay, so image verification entry means the DB need to report the PKCS algorithm for the DB if you use a PKCS 7 certificate. It's a detailed algorithm OID used in a PKCS 7 certificate. UEFI secure boot authorization DB is it will report EFI signature list supported by this firmware. For example, I list the CERT X59 and the CERT SHA-256, SHA-384, SHA-512. The first one, X59, is the PKS7. The detailed algorithm in this X59 PKS7 will be reported in the image verification table. But the SHA-256 and all the rest of the SHA algorithm just reported here because it's just a SHA algorithm. You already get that information. And there are also 3 entry gray out, means it is not supported today, but we plan to support is X59 SHA-256. That is a to be signed certificate hash.
To add a little bit more there, right? So the image verification is actually verifying the binary that we're trying to launch, right? And how it's signed. And since that's done with, PKCS7 verification, that's OID based. But when we're talking about secure boot authorization, that is the UEFI algorithm that goes and looks to see if the trust anchor is matched in the database, in the DB. And so we have different ways to match that with different signature list types. And so we have to be able to declare what types we understand and know how to do a match on.
All right. Well, with that, we are at about time here. So the slides will be posted on the UEFI Forum website, and a video of this will be available after the webinar wraps up, as well as on the UEFI Forum YouTube channel. Thank you, everyone, for joining today. And thank you, Sean and Jiewen.
Thank you.